Alright, welcome back. We are looking at Module 8, Inquiry Question 1. I'm going to cover through a couple of dot points here today. We're going to look at the production of emission and absorption spectra and compare this with blackbody radiation spectra. We're going to investigate key features of stellar spectra. What we mean by stellar is stars, so we're going to look at the spectra of stars and look at how these are used to classify stars in terms of their size, the brightness, the shapes. And we're going to look at Hertzsprung-Russell diagram and how it's used to determine certain characteristics of the stars, what stage of its evolutionary cycle is it in, the surface temperature, color, and luminosity. So our reference point today is the following numbers, and as you can see, we're looking at to investigate how radiation transforms into matter. Not actually that, but we're looking at what stellar spectra can tell us about the star. So just to quickly revise through, when we first introduced the idea of absorption spectra, this was the image we used. And we also have three types of spectra here. So the first one we have here, that is absorption. Second one we have here, that's emission. And the third one up here, we call this the continuous spectrum. Or another way of calling it is the black body radiation spectra. Okay? So the reason why we call it continuous, or why we say it's black body, remember black bodies emit all sorts of wavelengths of light. And so it is going to emit the entire rainbow of colors you see here. Alright, so let's start off spectra and black body spectrum. Okay, just revising on what we did in Module 7. We firstly said that a continuous spectrum contains all wavelengths of the visible light spectra. Emission spectra occur because photons of specific frequencies were emitted during an electron transition. So that's the key word, emitted. Absorption lines, or the absorption spectra, these occur because the photons were absorbed. So it's due to an absence of photons of a specific frequency. So there's that. Now, what actually shows us this? Well, it comes to a guy called Niels Bohr, which we'll learn about later in Inquiry Question 2 and 3. He came up with the idea that inside an atom, there's a specific, or if we have a look, so we have our atom here. Let's call this shell number 1, shell number 2, shell number 3. He basically said that each energy shell is quantized. So this has a specific energy. This also had a specific energy. This also had a specific energy. If you were an electron, okay, you had to stay in that specific energy level because that's the amount of energy you have. Should the electron want to go up an energy shell, or should the electron want to come down an energy shell, it needs to give off energy. Okay, so let's quickly look at what Bohr's atom kind of tells us. Okay, so using the evidence of hydrogen spectra, which we have already, this is actually these colors of the hydrogen spectra you see here. Niels Bohr proposed that the concept of quantized energy states. So the idea is if an electron wants to transition between energy levels, the energy that's absorbed or gained has to match the energy gap. So here we have energy level 2 and we have energy level 3. When this electron is coming down, it is going to emit some form of electromagnetic wave. The reason why it releases electromagnetic waves or radiation is because energy 3 has more energy than energy 2. Okay, so the total energy released, which is also the energy of our photon, in this case is the energy difference of level 3 subtracted by level 2. Okay, obviously you know that the energy released by the photon is hf. So these transitions are quantized. What that means is this has to be whole number changes, or an easier way to put it is if that energy transition is in between this gap. Okay, so say this energy gap was 2 and we got 1.5, then there couldn't be a transition possible. Okay, now for the larger transitions, so let's say from 6 down to 2, that will result in more higher energy photons, so it's a higher frequency, lower wavelength being absorbed or emitted if we're moving up or down, that is. Okay, and in order to achieve the emission spectra for visible light, this transition needs to be from some really high transition all the way to the second shell of the atom. If it was any lower, you get ultraviolet light. Okay, another way you can sort of think about quantized energy levels is imagining electrons trying to jump stairwells or staircases. In order to jump up the staircase, it needs energy to jump up. If you don't give it enough energy to jump, it can't make that transition. So I could give it a bit of energy boost, I could kind of push it up, but if it's not enough to reach that particular height, then the electron doesn't go anywhere. Okay, next we have the formation of the absorption spectra. So like we said before, in absorption, what's actually happening is a photon of a specific energy is going to be absorbed by the electron. Now, if the energy of the photon matches the energy gap, let's in this case call this energy 2, this is shell number 3, if that matches that energy gap there, then our electron can move up. When it moves up, because we've used a specific wavelength, so with frequency we know that it is proportional to wavelength, then we've lost a specific wavelength of light in our spectra. So if you have a look at helium here, that means at this point here, this point here, this point here, all the black lines that you see, a specific wavelength of light was absorbed. And because of that, the electron was allowed to move up the energy shell. Next one we have is emission spectra. So we have the issue of if we have a excited electron, so one that's already migrated up, it's going to relax at some point and it's going to release some energy. So it's going to come down like so. Now here we have energy level of 5 and we're going down to energy level 2. So that means the energy of the photon we release must be the difference between these two, and that releases your electromagnetic radiation. Obviously the higher the transition, the shorter the wavelength, higher frequency. So from 5 to 2 we get violet light. If it was from 3 to 2 we get red light there. So that's where we see all these different colors. Okay, blackbody radiation is slightly different. Obviously it emits all colors of the spectra. The other difference we know is to form blackbody spectra, it is temperature dependent. Now we know from Wend's law that the maximum intensity wavelength is B over T, and so the higher the temperature, the smaller the wavelength we get as the maximum intensity spectra. So it's going to release more photons on the shorter wavelength spectra as you increase temperature. With emission and absorption spectra, you don't need temperature as a factor, but blackbody radiation is temperature dependent. Okay, so as we said there. All right. So just remember, in terms of the area curve, the greater the temperature, the greater intensity of light is produced, while as emission and absorption spectra is to do with the transitioning of electrons in low temperature states. Okay, because if it's low temperature, there is no emission of light out in the same way that black body does it. Okay, so black body absorbs all thermal energy and it will release, causing atoms to oscillate, releasing energy, electrons for emission and absorption spectra, that is transitioning between the energy shells. Okay, so there's that. If you want to see any kind of difference that you see, where can we produce that? Black body radiation, really hot objects under immense pressure, emission spectra, low density gases like LEDs or LED incandescent lights, that produces emission spectra. Absorption spectra is when you expose white light in front of a cool gas, that absorbs the energy. Okay, next we're going to look at how we classify the stars. So how do we use these absorption and emission spectra to work out what's exactly in a star? Okay, well, the first thing we know is depending on the temperature of the star, because the star is similar in the way it manufactures light, like a black body spectra, we actually categorize it in a couple of different classes: O, B, A, F, G, K, or M. Okay, and the way we classify this is based on the luminosity, so the intensity of the light produced by the star, and also its temperature. If you actually have a look here for the biggest category stars, so big stars obviously mean it has a higher temperature and it's also brighter. They produce more light in the blue to ultraviolet region. If we have a look at the medium mass stars, they tend to produce more green colors, so closer to the green spectra. Those usually get registered as white light because you have a nice balance between blue and red. And obviously the more dull looking stars, the ones that have a low temperature, will be more closer to the red side of the visible spectra. Okay, so what do we actually see, or what can we actually tell from these particular spectra features? Well, we can work out its spectral class. So this will be a nice little hint of, if we know what class it's in, so A, B, O, all those kind of things, we will probably know what the surface temperature is, so surface temperature. We can also work out the color, because we know that temperature will give us the wavelength, or the maximum peak wavelength, and so we can also work out the color from there. In terms of the thickness of the line, so you can see the absorption lines here, okay, the thicker these lines are, it means the greater abundance of elements we have. It also can help us determine the luminosity or brightness of the star. And obviously it can tell us about the density of stars. So denser stars, more compact stars, will have thicker absorption lines because there's a greater opportunity for these photons to be absorbed by the atoms. Obviously the other thing we can work out is if there is any absentees in the absorption lines or presence of the absorption lines, we can also work out the chemical composition of the star by comparing it to other absorption spectras on Earth, and that gives us a nice little entail of the blueprint that all the chemicals and all the elements that make up the star. Okay, so if we actually have a look at the chart here, we go from 2,500 Kelvin all the way to 5,000 Kelvin. This is surface temperature we're dealing with here. if you have a look at obviously the different temperatures, remember, according to Wend's law, the higher the temperature, the lower the wavelength of light we produce. We know that blue light has a smaller wavelength than red light, so that's been consistent with what we've seen with Wend's law here. Okay, so as you can see, about 2,500 to about 5,000, we go from red to orange. From 10,000 to 50,000, we go from blue-white to blue. Again, like we said before, the reason why there's a region where the stars are appearing to be white is because we have equal intensity of this side of the spectra with the blue side spectra. So that's what we have here. One way they try and tell you to remember it is, oh, be a fine girl, kiss me. Obviously, there's bound to be better ways to remember it. So, you know, if anyone knows a better way, please write it down in the comments below and I can always change it. I do feel like there are many better ways to sort of remember this particular class without working out that way. So, what can we conclude from this? We know that the spectral class will tell us the color of the stars. It will also tell us the temperature that the stars belong to. Our sun belongs around this region here. So it's I don't quite remember where, but it's about a class K or class M star. Very small. Okay, so what can we actually tell from the intensity of the absorption lines? Well, actually speaking, originally these stellar spectras were classified based on the amount of absorption lines that we saw from hydrogen. So what we predicted was O stars would have a greater amount of absorption lines on the shorter wavelength spectra, and hence that's how we classified them, basically. So that's how we actually originally put these into categories. We have changed it a little bit in terms of brightness and surface temperature, but originally it was based on how much absorption lines to the hydrogen spectra was available. Another thing we can actually work out is the chemical composition. So we find that the stars classified in O tend to have more ionized helium. Essentially, ionized helium is helium that doesn't have that is charged. Neutral helium is helium that has a net charge of 0. Hydrogen for class A, ionized metals class F and G, so on and so on. This is a nice little table that can tell you what's all the different information of the spectra can tell you. Obviously it says attachment, so if you are watching this and you are in the class, you will have a copy of this with you. So O, that tells you the rough surface temperature. Remember, it is surface temperature, not core temperature. The core temperature of these stars would be a lot bigger. They tend to be blue, have a lot of ionized lines, and has a strong UV component in the spectra. So there's that. And so yeah, as you can see, no need to go through each one at a time. You can by all means read this, but based on the spectral class, we can work out the temperature, color, and the features. So it's quite handy. Okay, if you actually have a look at this chart here, we have 3 different types of spectral classes. Star X, you can see that there's a greater quantity of red, red, how do we put it? Red in the visible spectra, or there's more red light in terms of quantity. So Star X would appear more red. Star Y will appear more yellow-white. So you can see that in terms of consistency here, there's about the same quantity of blue light and red light photons, and then green and yellow photons. So you would expect this to be more yellow-white. Star Z, you can see that there's a greater quantity of blue light here, so we would expect that the light would be more blue, or the surface of the star would appear to be blue. If we're trying to predict the surface temperature, obviously all you use is Wend's law. So just to give you an idea, I won't do all the calculations because you can see it on the next slide, but using Wend's law we know that the maximum wavelength is equal to B over T. So what you do is you find where the maximum point is. Let's say this point here. Okay, I'm going to say that the maximum wavelength is around 600 nanometers. You're going to find the constant of B, which is 2.8. So that 10 to the power minus 9 equals T 2.89 10 to the minus 3. Switch over your equation, you should find a nice value of T, or temperature, in Kelvin, and that'll tell you the surface temperature. As we said before, if it is a blue star, it's most likely to be in the class B or O, depending on, but we'll have to check the temperatures there. So let's have a look. So the temperature we saw for star Z is 7,500. It could be star A or B, so as you can see here, in that category, star A there. Okay, so that's kind of how we make it all come together for us. Alright, so the last bit we're going to look at is Hertzsprung-Russell diagrams. The Hertzsprung-Russell diagram looks something like this. Okay, you have on one side absolute magnitude, luminosity. Don't worry about what both of these, or what's the main difference. They're both measuring the intensity of light. Okay, so we're saying for the brighter stars, its absolute magnitude is a negative value, while as the dimmer stars have a positive absolute value there. Okay, so there's that. We also have on the x-axis temperature and the spectral class. Remember what we said before, temperature can be directly related to your spectral class. So the higher the temperature, the higher the spectral class organization you get here. So O will always represent the higher temperature, M will represent the lowest temperature. So as you go further left of this Hertzsprung-Russell diagram, the higher the temperature of the stars you'll see. Our star belongs around this region here. When it dies, basically, it is going to migrate and become a giant, and once it's done, it's going to migrate and become a white dwarf. And that's kind of how it works in this particular cycle here. Okay, so this is what we know. Depending on the size of the star, we might eventually get a white dwarf, or we might get a black hole, neutron star, supernova, those kind of things there. Okay, so that's what we have. Our star is in the main sequence right now, or our sun. When it dies, it will become a red giant. Basically, during this process here, we get an incredible expansion of the star, and what scientists predict is it's going to engulf all the terrestrial planets from Mercury all the way to Mars. Depending on the size, if it's a small mass star, low mass star, it becomes a nebula, planetary nebula. If it's a big mass star, you eventually get to a supernova and then a black hole. Okay, so that's what we have here. Supergiants is actually the term we use for the really big main sequence stars that end up dying, and then the red giants tend to be the smaller stars. Okay, so with red giants we have nuclear fusion of helium to carbon. With supergiants we have lots of different types of nuclear fusions in the cells, forming all the way up to iron in its core, whilst white dwarf has no nuclear fusion whatsoever. Okay, let's have a look at one of these questions on the Hertzsprung-Russell diagram. It says, in which region would a star have the same surface temperature as a star in the main sequence? So this is our main sequence. Okay, so it's saying which one will have the same temperature. Well, by elimination of choice, if you can actually see, S would be your only valid option, as R, Q, and P, none of them are in the same range as the main sequence stars. So the actual answer for this is D. According to the HSC NESA website, this would be equivalent to a band 2 or 3. Okay, so next one, we have stars in region S of the diagram are much dimmer than other stars in the same spectral class. So region S here. Okay, in comparison to these stars here. As you know, this is our white dwarfs, and this is our main sequence stars here. So maybe I'll just write that down. So this is the white dwarf, that's when low mass stars die. And this is our main sequence stars where our sun is currently at. Okay, so what property of the stars in region S explains their relatively low luminosity? Okay, let's have a look. They are cooler than other stars. Okay, so remember what we said, if it's on the same x-axis range, it's the same temperature, so that can't be correct. They have smaller mass than other stars. Okay, not exactly either, because it's going through nuclear fusion, so you still have a similar kind of mass going on here. There might be some mass defect here and there, but it's relatively similar. They have a smaller surface area than other stars. Okay, this one is more on point here. So what actually happens is white dwarfs have a small surface area than the main sequence stars, and obviously the red giants are the biggest. So when the star begins to die, the fuel source causes a great expansion of energy, and then that great expansion causes a collapse. So gravity is pulling all this pressure back into the star, and it causes the formation of this small white dwarf here. Okay, so if it has a low surface area, okay, then that also means it will have a much dimmer representation, so it looks less bright overall. Okay, so that's what we have here. Okay, so that kind of concludes what we talked about with luminosity, temperature, and color of stars in the HR diagram. Hopefully you enjoyed that and worked out everything you need to know. There are a couple of questions, so you can pause it here and answer. I'll move on. And another 2 questions you have here, which again I'll move on now. And so there's that. So we have a little summary of everything you need to know about the HR diagrams. Please replay the video or read through this summary here to give you a little bit more context if you need that additional revision or help. And that basically concludes our lesson about star spectras and also how HR diagrams tell us the characteristics of different stars. Until next time, I hope you enjoyed the video. Hopefully you found it informative. But like I said, until next time, study hard and keep cracking on.